Hello, and welcome to Astronomy 100. In the previous section, we were talking about how light has a particular speed that it travels at, and how that speed that light travels at is enormously fast, but it is a constant speed. Light always travels at one speed as it travels through our universe. And because light requires time to travel distances that are very, very big in astronomy, that means that we're forever looking at objects as we were to see them in the past. It takes time for the light to reach us. And the example that we ended with last time is the one that I want to start with here today. And if you remember, when we look at a distant galaxy, such as this one called M51, admittedly not a very romantic name, but this particular galaxy we're looking at such a tremendous distance that the light has taken 23 million years to reach us. This consequence provides a way for us to use this phenomenon to indicate a unit of distance. And this is the most familiar, the most common unit of distance that we have in astronomy, and that is the distance called the light year. So let me define it for you. 1 light year is defined as the distance that a beam of light will travel in a year's worth of time. Be careful with this definition because although the term light year indicates a unit of time, it is actually a unit of distance. So the idea is if we were to go outside and let a beam of light loose to let it go off into the universe, after a year's worth of time, if we measured how far that it traveled, that distance would be 1 light year. And we've already seen in a previous section that over the course of 1 year, light travels 5.9 trillion miles. And the difference this time is we're going to write it out for you so you have a full appreciation of just how far 5.9 trillion miles is. So 1 light year is a distance of almost 6 trillion miles. And that now becomes a standard distance unit that can be used in a variety of ways. So let me show you a few examples of how we're going to use this unit of the light year in some of the examples we saw in the last segment. When we look at the stars of the constellation of Orion, an example is when we look at the star Betelgeuse, we are seeing it the way that it looked 427 years ago. And since light takes an enormous amount of time, 427 years to travel that distance, we can say the distance to Betelgeuse is 427 light years. Now, if you want to know how far that is in miles, you would simply multiply 427 times 6 or 5.9 trillion miles. So when you multiply those two together, it's an enormous distance if we use the units of miles. So astronomers need a unit of distance that's much bigger to talk about these very big distances. And it's a lot easier to say 427 light years than to refer to the trillions of miles that it is between one object and another. Here are a few more of the examples. Rigel is a distance of 773 light years, and the Orion Nebula, this part right here, is 1,600 light years in distance. If we go back to the galaxy M51, we now say that this galaxy is 23 million light years in distance. Now imagine that number, 23 million multiplied by 6 trillion is an enormous number. So even the galaxies that are fairly close to us, such as this galaxy here, are at tremendous distances so that the light coming from this galaxy has taken an enormous amount of time to reach us because the distance is a tremendous distance. So light has a speed and it takes time to travel from one place to another. The next question is, in what manner does light travel? In other words, how does it go from one place to another? And when it comes to the explanation, we have to remind ourselves that light is energy, and when energy goes from one place to another, there's actually 2 basic ways that energy can go from one place to another. So let's look at the 2 choices. What we have is, one option is when energy travels in the form of a wave. And I have 2 examples for you here. The first one is this animation you see here on the screen. This is an example of sound waves. So the speaker is basically moving in and out, in and out, and in and out. And by doing so, it creates what's called a pressure wave. and it causes the air to get pushed and pulled and pushed and pulled. And so the energy of the speaker is transferred to the air in the form of a wave. And that's how you hear sound, is when that wave enters your eardrum or enters your ear canal and makes your eardrum bounce back and forth. That's translated into sound. So energy can travel as a wave, such as what is done here with a speaker. Another example is simply waves on the ocean. These waves that you can see coming into the shoreline have traveled tremendous distances. Usually the waves that come into the shoreline have been traveling for thousands of miles in some cases. Some very distant storm raging over the ocean has ended up allowing that energy of the storm to get transferred to the water. And then that energy travels through the water in the form of the wave. And then eventually the wave breaks on the beach. So energy can travel as a wave, or energy can travel as a particle. The best example that is kind of a simple one is this high-speed photograph of a very powerful, very fast bullet that is being shot through an apple. And you can see that as the bullet enters the apple, passes through the apple, and continues on its path, there was a tremendous amount of energy that the bullet gave to the apple. But the idea is the bullet is carrying the energy. So when the bullet is shot out of the gun, the bullet is given energy. The bullet then carries that energy across the room. Anything it encounters along the way, it gives a little bit of its energy to the apple in this case. So the bullet is the carrier. Notice it's not a wave. The bullet itself is as if it's a particle that is carrying the energy. The bullet is the particle carrying the energy. So the question is, which one of these two options is what light is doing? And historically, the person to begin to unravel the details of this is a familiar name. It was Isaac Newton. Isaac Newton, of course, is somebody who is very famous for his contributions to science. But when it comes to the field of optics, he made some important discoveries. For instance, Isaac Newton, when he lived in the ancient times of England, actually 300-400 years ago, he lived in the countryside of England, and he had a home that he did a lot of his experiments in. And one of the rooms in his home that he had a bank of windows that faces the sun in the late afternoon. And so he has some shutters that are built to cover these windows to keep the room from being flooded with sunlight, something that's obviously quite annoying if you've ever had a home with a room facing the sun. But these shutters, of course, had little cracks and crevices that allowed the sunlight to pass through. And in this picture here, you can actually see an artist's impression of this concept. And so you can see that in his laboratory, he had various places where sunlight would enter into the room. Well, Isaac Newton was somebody who was doing some work with cut pieces of glass that we call prisms. Just a very, very normal looking prism. I'm sure you've seen one before. And you can see in this portrait that he's holding a prism up to one of the shafts of sunlight, and he is casting across the room. He's casting what we'd call a rainbow. Now, of course, this is nothing new. It's not something that had never been done before. But what Newton was able to do by doing it in this fashion is he was able to create a controlled environment where he could create a rainbow, and then he would have the ability to study the details of that rainbow. And he was able to discover some very critically important things about light, in this case, in the form of a rainbow. So let's look at what he found. This is a really nice photograph of in a laboratory with the lights off. Here is a prism sitting on a table, and this is the top-down view. So imagine a camera suspended over the prism. And then light comes in from one side, passes through the prism, and it comes out as what we would call a rainbow. And if you had a screen set up right here, you would, of course, project a very, very nice-looking rainbow onto that screen. What Newton discovered was some interesting things. For instance, he noticed that every single time he produces a rainbow in this fashion, regardless of the type of glass that he used, the colors were always in the same sequence. So the order of the colors never seemed to change. They're always the same order of colors, such as you see here. The other thing he noticed is that the variation between colors seemed to be very gradual. So there's no one specific place where you can tell that the red ends and the orange begins, or no place where the green ends and the blue begins. It just seems to be as if one color transitions to the next color, transitions to the next color. Something that's rather interesting and also very difficult to reproduce if you were to try to make a rainbow artificially. The next thing that he discovered is that when you notice where the red begins, it's not a very sharp line. It's as if the black just gradually becomes brighter and brighter until you have red. There's no cutoff right there that you could point to. Similarly, where the violet seems to fade to black, there is no cutoff. And Newton suggested maybe there is actually something on the other side of the violet that we're just not seeing, or maybe there is something just before the red that we're not seeing. And it turns out, of course, that he is correct. So the colors of the rainbow were something that allowed him to discover some interesting things about the rainbow itself. And I'm going to introduce some terminology to go with this, some important terminology that we're going to use as we continue through this section. So let's go back to this picture here and I'll show you what I mean here. First of all, the light that is entering this prism is what we call white light. And eventually we'll explain more specifically what that means. All I'll say right now is it's not simply as trivial as it may sound. The white light enters the prism and of course comes out as the rainbow. In physics, we often don't say the word rainbow. And the reason why is because you'll notice there was no rain that was used to create this rainbow. So a rainbow in the world of physics is what you get outside when the rain creates a rainbow. But in this case, you get these colors in a variety of different types of colors arrayed in order that you see here. And so we actually refer to this as a continuous spectrum of color, or sometimes we simply call it the spectrum. And in the context of the astronomy class, I will continuously use the phrase visible spectrum. So I'm going to really start to get away from the word rainbow and start to say visible spectrum. So make sure you understand the terminology of that. This is the visible spectrum. And then one last thing that's needed for students of astronomy is they need to learn the order of the colors of the rainbow, and they need to know the correct colors, of course, in the correct order. So officially, the rainbow, or the visible spectrum, is composed of red, orange, yellow, green, blue, and violet. So those are the official colors of the visible spectrum. And what we often do is provide a way for you to remember the colors in the correct order by giving you what looks like a very strange sounding name. This has been done for decades. The name Roy G. Biv is a way to remember the colors in the correct order. For instance, R is for red, O is for orange, Y is for yellow, G is for green, B is for blue, V is for violet. So it looks as if it's somebody's name, Roy G. Biv. The lowercase I is from in the days of at least a while ago with the physics of light. It was at one time indicated that indigo was a separate color, but that has changed. So Roy G. Biv, red, orange, yellow, green, blue, violet. Now the last thing that Newton was able to do was do a really interesting experiment. And what he was able to do was to take the light, pass it through a prism, and then of course get the rainbow or a visible spectrum out of it. But what he then did was he took another prism and he allowed the rainbow to pass through the prism. And what he got was this. White light goes into the prism, comes out as a rainbow, but then when that rainbow goes into another prism, it basically is turned back into white light. So notice white light becomes a visible spectrum and the visible spectrum goes back to white light. And according to Isaac Newton, this demonstrates that light must travel as a particle of energy. His logic was that light must be composed of all of these different colors, and each of these different colors are like particles of light. And the reason why he used that logic is because particles have the ability to be sorted out. Only particles can be sorted, such as coins in your jar at home can be sorted into different denominations, or maybe various pieces of candy that you like can be sorted in different styles. Different particles have the ability to be sorted. And so when you put all of these light particles together of all these different colors, you get white. But when you pass the white through the prism has the ability to sort out the individual colors. And so therefore, this demonstrates that light is behaving in a way as if it's traveling as a particle of energy. And it turns out that this is a correct interpretation. So Isaac Newton shows that light travels from one place to another as if it is a particle-like entity, a carrier of energy, traveling in the form of a particle. In the next segment, we'll talk about other interpretations. I hope you'll join me then.